Hello and welcome to this section of the Chemistry Tutor. In this section we're going to continue our discussion of redox reactions, and specifically we're going to talk about using the half reactions and figuring out what is being oxidized and what is being reduced from the half reactions. Because again, you can have a long redox reaction. What we're doing with the half reactions is breaking it up into two half reactions. One of those reactions is going to be an oxidation process. The other is going to be called a reduction process. And so you have to have oxidation and reduction going on at the same time in your redox reaction. So when we split the big reaction up into half reactions, we should get one that's oxidized and one that's reduced. So let's just take a few examples of these little half reactions and see if we can figure out from looking at it if it's an oxidation process or if it's a reduction process. And the first thing I want to do before I get there is just say that I have replaced our definitions of oxidation and reduction on the board with these sort of simplified definitions, sort of like just abbreviated a little bit to get them on the board in a small space, and I'm going to leave these up because I really want to drill this in. So just to refresh your memory, the oxidation process is when you lose electrons. That's what we call the process of oxidation, is when something loses electrons. If something is undergoing an oxidation process, it's also called a reducing agent in the reaction, because a reducing agent is the thing that donates the electrons. If something's undergoing reduction, that means it's gaining electrons and accepting those electrons, and because of that, it's also called an oxidizing agent. That item that we're talking about, whatever's being reduced in the reaction, is called an oxidizing agent because that's the thing that's accepting the electrons. I'm trying different ways to explain this to you so that you can kind of get the point across, but the bottom line is you have oxidation, losing electrons, reduction, gaining electrons. These agent definitions are just another way of renaming the exact same thing. And you have to learn both of them when you talk about chemical reactions in the redox world, because a lot of times your book will talk about the oxidizing agent or the reducing agent, and you need to know what they're talking about. So let's get started. Let's look at a reaction real quick, a half reaction I should say. What if we have lithium, which is a positive ion? Let's say that we have something like this. And the question I have for you is this an oxidation process or is this a reduction process? Well, here we have lithium ion, so it's already a positive charge. An electron comes along with that lithium ion, and out comes a neutral lithium atom. So we have a single +1 charge here, we have the electron, which is -1, combining, we get a neutral result. So what we have is some item that is accepting electrons. It's gaining an electron in this process. So this is going to be called a reduction process. So that's what we need to write down. So this is called reduction. Really, in order to identify oxidation or reduction, all you have to do is look and see, is the item you're talking about taking in electrons, or is it donating electrons back into the solution or whatever we're talking about. So let's say number 2. Let's say we have 2 iodine ions, and that just yields I2 plus 2 electrons. Iodine is one of those diatomic molecules. Usually you see it exist as I sub 2. So what we have is, and this is balanced, notice, because we have 2 iodines, and so on. So what we have to figure out is from the reaction here, is this oxidation or is it reduction? Well, we have a species, and what we see is, yes, we end up with a neutral guy, but what ends up happening is some electrons split off from the original ion we start with. So some electrons are leaving the scene of the crime, so to speak. So we're losing electrons. And because we're losing electrons, this is called an oxidation process. And you can see that from over there. So oxidation. So basically in these half reactions, if you see electrons leaving the scene of the crime, we start with something and then you end up with something electrons are leaving. That's losing electrons. That is electron donation. And so that is oxidation. All right, now what if we have H2 yields 2 hydrogen ions plus 2 electrons? Now make sure you understand what's happening here. We have H2, that's a diatomic molecule, 2 hydrogen atoms bound together. And then we have the reaction where 2 of these electrons peel off because we have 2 hydrogen atoms. 1 electron comes from each of the hydrogen atoms there. What we're left with is 2 hydrogen ions. So 2 electrons peel off, 1 from each atom, so we're left with 2 ions, each with a charge of +1. Because if you look at your periodic table, Hydrogen really likes to be +1 when it can because it's in that first column there. And each of these ions does have a charge of +1. But is this an oxidation process or a reduction process? And if you look at it, the original species we have is electrons are leaving the scene of the crime, changing it into something else. So they're off going on to something else, so this is oxidation. It's an oxidation process because this hydrogen atom is losing electrons. And then finally, let's say we have something like iron with a charge of +3 plus an electron gives this iron with a charge of +2. Is this oxidation or is this reduction? This is a little different because we're starting with an ion and we're ending with an ion. But notice what's happening. This has a charge of +3. This means that in this state, iron, which is a neutral atom, has already lost 3 electrons. That's why it's +3. So we gain an electron here, and when we do that, we change the charge from +3 to +2 because we have one more negative charge in there, and that's going to change the net charge on this guy back up to +3. If we had gained 3 electrons here, it would make this iron neutral again, but we did not gain 3 electrons. We only gained 1. So we still have a charge on the iron, but it's a +2. It's getting closer to 0 as we add these electrons back in. So since this guy is accepting electrons or gaining electrons, then we call this reduction. So here I'm doing 2 things with these sorts of problems. The first one is we're identifying oxidation and reduction, and you can tell that straight away just from how it looks. Here you're gaining electrons, so it's a reduction. Here you're losing electrons, so it's oxidation. Here you're losing electrons, so it's oxidation. Here you're gaining electrons, so it's reduction. And the second thing we're doing is we're learning how to read these half reactions. To see the charges, you know, up until this point in chemistry, haven't seen a lot of ion charges in our reactions. But this is what this is illustrating. You know, hydrogen is 2 atoms. We get 2 hydrogen ions plus 2 liberated electrons. So it's giving us an opportunity to study that and learn how to read these half reactions. So I want to do 2 things with the next set of problems. I'm going to put a reaction on the board that's not completed, and I want to figure out how to balance it, how to make it make sense. And then I want to figure out if it's oxidation and if it's reduction. And also, is that species an oxidizing agent or reducing agent? So we're just using our definitions. You know, and definitions is 99% of everything you learn in chemistry. So let's say you have some chromium, which is a solid. And let's say it ends up becoming chromium, but with a charge of +3. And let's say this is an aqueous solution. Okay? Now, there's obviously something missing here because you can't just spontaneously go from having a neutral atom of chromium to an atom with a charge of +3. Something has to happen there in order for the new ion to have a charge. What needs to happen? Well, this chromium needs to lose some electrons. So if it loses those electrons, then it's going to have a net positive charge. How many electrons does it need to lose? Well, it's pretty clear because this is a +3 charge. What needs to happen is chromium really is going to end up being 3 plus 3 electrons. This is a balanced half reaction. The reason we call it balanced is because it's balanced with respect to both the atoms. See, we have 1 chromium atom here and 1 chromium atom there, but also in regards to the charge, because here we have a situation where we end up with an ion and we have to account somehow for how this ion came about, and so this guy liberates 3 electrons there. So we have a balanced half reaction here because we have the atoms balanced, the chromium's balanced, and we're taking account to what's going on with the electrons. 3 electrons are gone away. Now, is this oxidation or reduction? Well, this is a situation where chromium is losing electrons, right? It's losing electrons because it started with a neutral atom. We end up with an ion plus some free electrons. So this is an oxidation process. Okay, this is a process of oxidation because chromium is losing electrons. Now the other question is the chromium atom that we started with, is it an oxidizing agent or a reducing agent? There's 2 ways to do this. The easy way is just once you figure out if this is an oxidation process, you automatically know that it's a reducing agent. And you know that because of the way these definitions are set up, but once you know it's an oxidation process, you know that what we're talking about here, the chromium, is automatically a reducing agent. I told you that before. Once you figure out what kind of process it is, just flip to the other term, and that's the agent that you have. So it's a reducing agent. And to convince yourself it's a reducing agent is whatever we have in the reaction that's donating the electrons. It's just another word to say, when you have a reducing agent that you're talking about, it's just another way of saying that that thing is being oxidized. Because when something's being oxidized, it's giving up electrons, which is exactly the same thing that we call a reducing agent. They're kind of synonyms, really, is what it is. So that's what's going on here. So chromium is the thing that's donating the electrons, so it would be the reducing agent. Now, this is only a half reaction, so we don't see the other half. We don't see where these electrons are going and combining with, because this is just a half reaction. But in a real reaction, this would be the oxidation process, and then we would have another half reaction which would take those 3 electrons that are liberated, and there would be another process that would be a reduction process where those 3 electrons would be coming in and being gained. So this is just a half reaction here. Okay, so let's go and do another guy here. Let's say we have nickel with a charge of +3. And let's say that we end up getting nickel with a charge of +2. Now obviously there's something missing here, because anytime you have an ion that has a charge that's changing, there has to be something going on with some electrons along the way here. Okay, now this is a positive charge. The only way I can make it less positive like this is if I end up adding electrons. So here I have, let me go ahead and switch colors to make it a little bit clearer. We'll do red like we did last time. So if I have nickel 3+, all I have to do to it is add an electron to get me nickel 2+. Make sure you understand that. So here I have +3 charge on my nickel. So that means this nickel is a neutral atom that's lost 3 electrons. If I add one of those electrons back, I'm gonna go less positive, so to speak, more towards neutral, and I'm going to end up with a charge of +2 on the nickel, because every time I add electrons back in, I'm making this thing more and more neutral. So I come down a level to +2 like this. So the question is this an oxidation process or is this a reduction process? Well, if you look at our definitions, oxidation is when we lose electrons, reduction is when you gain electrons. So here I have this nickel ion, it's gaining an electron, so clearly this is called a reduction process. All right, this is a reduction process. Now, is this nickel ion that we're looking at, is this an oxidizing agent or a reducing agent? And the easiest way to figure that out is to go and realize that once I know this is a reduction process, then I can say that nickel is an oxidizing agent. You know, just like up here when I said chromium, right here, is the reducing agent, the nickel ion, the thing I started with, is an oxidizing agent, because an oxidizing agent is just something that accepts the electrons. In this case, I'm accepting the electrons and I'm getting a new ion at the end of it. So this is a good introduction to half reactions, trying to understand what half reactions look like, and also basically balancing half reactions and trying to make them balance for both mass. That's what we're usually talking about balancing. We're trying to figure out, make sure the atoms are the same on both sides of the yield sign, but also trying to make sure that the charge is balanced. If this +3 ion somehow gets less positive, the only way that can happen is if an electron goes and jumps into this atom and takes its position in there. And if I add, in this case, if I take this guy and I add another electron to it, then this is going to be a +1 charge. And then if I take and add a third electron to that guy, then I would end up with a neutral nickel atom. All right, so make sure you understand the concept. Make sure you know how to apply the oxidation reduction definitions, to look at a half reaction, look at which way the electrons are going, and figure out if it's an oxidation or reduction process. Once you know the process, you automatically know if the thing you're talking about is a reducing agent or an oxidizing agent, because it's basically the opposite agent, okay? And that just comes from the way things are defined. Follow me on to the next section. We'll get a little bit more practice with half reactions and identifying if they're oxidation or reduction processes. Hello and welcome to the section of the Chemistry Tutor. Here we're going to continue talking about half reactions, trying to figure out if they're oxidation processes or reduction processes. In the last section, we just wrote the half reactions down, looked at how the electrons must be moving around, and from that figure out if it's oxidation or if it's reduction. Now we're going to continue along the same lines and basically deduce the same information but with the full-on ionic reaction written down. So let's go and do that. Let's write an example down and we'll see if we can figure out what's going on. What if we have 2 iron ions, aqueous solution, plus 10 an aqueous solution, all right? And that yields 2 irons in aqueous solution. These have a charge of plus 2, plus 10, and these guys have a charge of plus 4. So notice that this is not a half reaction. This is a full-blown reaction, but it's an ionic reaction because it's a reaction in aqueous solution, and all we see are the things that are changing here. As I've said many, many times before, I want to make sure you understand. You don't go to the lab supply warehouse and buy iron 3 ions in aqueous solution, typically. You don't go buy 10 ions with a charge of plus 2 in a bottle. You don't do that. When you see equations like this that have charges all over everything, those are what we already call net ionic equations. We've learned about those before. Basically, you might have some iron sulfate or something like that, and you might have some tin nitrate or something like that, and those are bound up, and those are what's on your shelf stable on your shelf. When you put them in water, they react, and then the other part of these compounds, like the nitrate or the sulfate or whatever it was that you got grabbed off the shelf, those are just the spectator ions that are sitting around in solution but not doing anything. So when we see a reaction like this, 2 iron ions and then 10 ions and then iron ions with a different charge and 10 ions with a different charge, what we're showing here is this is what's really actually participating in the electron transfer, in other words, what's actually happening in terms of chemistry. There are other things potentially floating around solution. You might have nitrates or sulfates or other things that were originally bound to these species up there, but they're not participating, they're spectator ions. And we've talked about that stuff in the net ionic part of the course earlier, so make sure you understand that. So you're going to very commonly see these net ionic equations with charges all over everything because they're occurring in aqueous solution. All right. So the question is, the first thing I want to do is split this up into half reactions. That's what the purpose of this problem is. I want to split it up into half reactions, and I want to identify which half reaction is the oxidation process and which half reaction is the reduction process. And so what I'm going to do to pull that off is start looking around. Okay, one half of this reaction is dealing with iron. Iron is changing charges. The other half of this reaction is dealing with the tin because it's changing charges. So that's our big clue. So we write down 2 irons. Of course, the charge is plus 3. All right. And then something needs to happen to make it into a charge of plus 2. The only way a charge of plus 3 can go to a charge of plus 2 is if we add an electron to it. And what we're going to get on the other side is 2 irons with a charge of plus 2. But notice, this isn't quite right. We're not just adding 1 electron here. I actually have 2 iron ions. If I only add 1 electron here, then it's going to take care of one of the irons I have, but the other one is not going to be affected because I have actually 2 iron ions. So really, this half reaction has a 2 here. So you need to kind of use your logic. What you see is the before and the after. 2 iron ions, 2 iron ions. Okay, each one of these is taking plus 1 charge from an electron in order to do what it's trying to do here. But since I start with 2 and I end with 2, it must require 2 electrons to do that. So it's up to you to provide that when you're writing these half reactions. So that's why we put the 2 in there. All right, and so what we do is we go down below and we will try, let me go ahead and put another line here. Let's see if we can write the other half of this reaction. So here we have 10, 2 plus aqueous solution, whoops, AQ aqueous solution, and that gives me yielding 10, 4 plus aqueous solution. So here's before and after. I have an ion with plus 2 and an ion with plus 4. How do I change from an ion with a positive charge to an ion with an even more positive charge? The only way that can happen is if I liberate some electrons and get rid of some electrons from this guy and then I have something that's even more positive. But how many electrons do I need to liberate? I have positive charge of 2, and then I end up with positive 4. So I have to liberate 2 electrons there, otherwise this is not going to occur. So when you're writing your half reactions, you're looking and trying to place where are the electrons going or coming, but also how many do you think are actually required? In this case, it takes 2 of them. All right? So the next question is, what is the this reaction above? These are the half reactions. Okay, this represents one half of what's going on. This represents the other half. You can see that this iron ion is accepting 2 electrons. It's taking in 2 electrons. And when you gain electrons here, that is a reduction process. So I'm going to write down here, this is a reduction process. All right? Now let's look at the next part. This guy, okay, this 10, is actually liberating electrons because after the reaction, electrons are floating off, so to speak. So it's losing electrons, and we've said many times that when you lose electrons, it's an oxidation process. So if you have a test, you might be given a reaction like this, and you might say, hey, write the half reactions, tell me which half reaction is the oxidation half reaction, and which reaction, a half reaction is the reduction process. So now you know enough to go figure out, okay, this is gaining electrons, so it's reduction. This is losing electrons, so it's oxidation. Now what if I ask you, what on the board here is the oxidizing agent, and what on the board here is the reducing agent, okay? So what we're trying to do is pick from what's on the left-hand side of the yield, which one of these is the oxidizing agent and which one of these is the reducing agent. And it's very easy here because now that I know this is a reduction process, I'm going to put a little semicolon, and I'm going to say Fe3 plus is, since it says reduction process, I'm going to call this the oxidizing agent. You just pick the opposite term, right? And since this is an oxidation process, then the 10 with the positive 2 charge is the reducing agent. And what is the reducing agent? It's actually the 10 2 plus. Okay? So whenever you're talking about is it oxidation or is it reduction, you're mostly just saying in this process what's happening. Is something gaining or something losing electrons? Fine. Okay? Then when you're talking about what is the oxidizing agent, what is the reducing agent, you're actually trying to pick something on the left-hand side of the yield arrow. One of these is going to be an oxidizing agent, one of them is going to be a reducing agent. In this case, this iron is the oxidizing agent because the oxidizing agent accepts the incoming electrons. And this is accepting the incoming electrons. And likewise, this 10 is donating electrons, so it's the reducing agent. The reducing agent is donating the electrons. Keep coming back to these definitions over and over and over again because they're so very important. All right, our final problem, just to kind of get more practice with this, what if I have zinc, which is a solid, plus 2 hydrogen ions, each charged plus 1, and I end up with zinc with a charge of positive 2 in aqueous solution plus hydrogen H2 gas, like this. All right. So this is, again, a net ionic equation because we see the ions present in here. And so presumably this H plus, prior to canceling the spectator ions, might have been tied up with something else. This zinc ion here might have been involved in something else. But what we're left when we see this net ionic equation is just the species that are actually participating. And what we can see here is that this zinc, okay, goes from a neutral atom into having a positive charge, and this hydrogen goes from having a positive charge into being a neutral gas. That's what's happening here. So if I want to write down the oxidation and reduction half reactions, let's just start with zinc first, okay? So what we're going to do is we're going to say zinc, okay, and on the other side of the equal sign, we're going to have zinc 2 plus aqueous solution. Now look at this and say, okay, this changes into this. How can that happen? This is a neutral atom, and then it becomes positive. So it has to liberate electrons in order to do that. How many electrons do you think it needs to liberate? Well, it needs to liberate 2 of them because I have a charge of positive 2. All right, so this is a half reaction. I'm going to skip a little space here and put a little line. And then I'm going to write in green the other half reaction. So what if I have 2H plus, and on the other side of the reaction I have hydrogen gas. Now how could this happen? I have two ions, each plus one, and somehow they become two atoms of hydrogen that are each neutral. The only way that you can do this is if this gains two electrons, because these two electrons are going to combine with these two ions, giving you two neutral hydrogen atoms, and anytime you have hydrogen, it's a diatomic, so it just always clumps together in terms of molecular hydrogen, in terms of molecule. All right, but this is the one of the half reactions. So the question then remains, which one of these is the oxidation process and which one of these is the reduction process? So let's go look at this. We have zinc changing into an ion and liberating, expelling some electrons. So it's losing electrons. So using our definition, this is an oxidation process. So let me just write it as oxidation process. All right. And then under here, if this is oxidation, you don't even really need to look at this in order to write that this is a reduction process. But if you wanted to check yourself, you'd look at this and say, well, this is accepting electrons. Accepting electrons, in other words, gaining electrons, is called a reduction. Now, if I also wanted to identify what species is the oxidizing agent and what species is the reducing agent, it's very simple now. Once I know that this is an oxidation process, this zinc on the left-hand side, zinc is the reducing agent. All right? And then, since this is a reduction process, this hydrogen ion I started with, H+, is the oxidizing agent. All right, so it's a little bit of a game of definitions, basically. You know, I mean, the main important thing is you want to know how to write these half reactions down and how to get the number of electrons in the right spot. Once you have them in the right spot, then you can claim, okay, this is losing electrons, it's an oxidation process. Since it's an oxidation process, zinc is also, by definition, a reducing agent because it's helping the reduction along by donating those electrons. This is a reduction process because it's gaining electrons. All right. It's also an oxidizing agent because it's the hydrogen is the guy accepting the electrons. So really, you know, these definitions, I understand this stuff really well, and they can still confuse me a little bit. So to be honest with you, what I do when I do these problems is I just write the half reaction down and I identify what is the oxidation process from losing electrons, and then I write down what is the reduction process by gaining electrons. So I write down oxidation process, reduction process. And then once you have this written down, you can flip to the other term and say zinc is a reducing agent, and this is, hydrogen ion is an oxidizing agent. To me, that's the easiest way, because the definitions, if you stare at them too long, can just end up confusing you for no good reason. Okay? So actually I'm going to do one more just to give you a little more practice with it. And that is, what if I have two irons, 3+ aqueous solution, plus 3 zincs, which is a solid, gives me 2 irons, which is a solid, plus 3 zincs, which is a charge of +2 in aqueous solution. So I want to do half reactions. Obviously, this is a net ionic already equation because I see my charges and I don't see much else besides ions and things. So here this iron is changing, it's changing charge, and this zinc is going from neutral to changing charge. The iron is going to changing charge over here. So if I want to write down the oxidation or the half reaction that's involving iron, I would say 2Fe3+. I've got to use my coefficients that I have. All right? And something's going to happen, and then I'm going to end up with 2 irons with a solid. Now, what's going to happen to the electrons? Here I have a +3 on each one of these irons, okay? And then I'm going to end up with a neutral iron atom. So let me ask you a question. If the 2's weren't here at all, if I covered them up, and if I'm going from +3 to neutral, how many electrons do you think it would take? Well, it would take 3 electrons to pile in here to make it neutral. It would take 3 electrons. But I don't have 1 iron ion. I have 2 of them. So instead of 3 of these electrons, it's actually going to take 6 electrons to do this. 3 of these electrons are going to combine and make one of these atoms, and the other 3 are going to go into there and make the other one. So you have to, when you're writing your half reactions, you have to look at the coefficients and really think about, with a real understanding of, okay, the electrons are leaving, and what charge are they? You got to figure that out and really get good at that so that you can put the right number here. Otherwise, you're just never going to get anywhere. All right, so that's one half reaction. Let me skip down a little bit and write down the other half reaction. So we did the one with iron, so let's go to zinc. 3 zincs, okay, and that's going to yield 3 zinc ions. Where do the electrons go? Here I have a neutral atom, and here I have an atom of zinc that has a charge of +2, or I should say an ion of zinc. If I cover up the coefficients like this, I go from having a neutral 0 charge on zinc to a +2. How many electrons does this zinc have to lose in order to give me a +2? Well, it'll have to lose 2 electrons in order to do this, right? 2 electrons. But I actually have 3 of these atoms doing this all at the same time. So it's 3 times 2 gives me 6 electrons that are actually lost. 6 electrons that are actually lost. So this zinc, each one of them is losing 2 electrons. Now I'm doing it 3 times over, so 2 times 3 is 6 electrons liberated. Notice, before I write anything on the board, in this process, or I should say in this process, I'm losing 6 electrons, but in this process, this guy is gaining 6 electrons. So it's kind of nice that one is losing 6 electrons and one is gaining 6 electrons. That has to be balanced like that in order for this reaction to actually work out. The number of electrons that you lose has to be equal to the number of electrons that is gained by something else. Okay, so that's just an important thing for you to remember. So which one of these is an oxidation process? And which one of these is a reduction process? Well, if we can go up here, you can see this is gaining electrons. And when things gain electrons, we call it a reduction process. So we call it reduction process. All right, and then we look down here and we say, okay, this zinc is actually losing all these electrons. And when we lose electrons, we've said it many times over, this is an oxidation process. Okay, so now we know which process is oxidation and which process is reduction. Now to find the oxidizing agent and the reducing agent is very easy. You've got to pick from what's on the left-hand side of the equal sign. This is iron with a charge of +3. So I say Fe3+ is, and since this is a reduction process, you can automatically just write oxidizing agent. You just pick the opposite term. Since this is an oxidation process, you can write down that zinc is the reducing agent. And again, it's all consistent with the definitions. A reducing agent is something that donates the electrons. This is donating these 6 electrons. So that wraps this section up in half reactions and identifying oxidation or reduction processes in a half reaction. So just don't forget the big picture here. We're given these long reactions, which is sort of like what we've got up here, okay? And we split it up into half reactions so that it's a little bit easier to see what's going on with the electron transfer, but also the kind of undercurrent that I haven't really told you too much about, but I told you a little bit, is that when you split these half reactions out, you can see how many electrons are gained and how many electrons are lost, and they have to balance. That's going to be a crucial step later on when we balance more complicated equations. You're going to be asked to make sure and write these half reactions so that these guys balance the electrons gained and lost, and that's going to be a crucial step to balancing these chemical reactions. So I'm kind of easing you into it. You know, right now I'm talking about reactions, splitting them up, identifying oxidation and reduction so you kind of get a feel for it, but just keep in mind that that's the direction we're going. So stay with me. Make sure you understand these problems, then follow me on to the next section where we're going to finally start to talk about oxidation numbers. And that's going to be a very important tool in helping us figure out also what's being oxidized and reduced in reactions, and is a nice segue or a nice lead-in to the real bread and butter of what we're trying to do, which is balance these redox reactions. Hello, and welcome to the section of the Chemistry Tutor. In this section, we're going to start to talk about the topic called oxidation numbers. Oxidation numbers, very important topic. It's going to help us learn how to track what's going on in a chemical reaction, which will lead us into being able to balance chemical reactions here in just a few sections. So up until now, we've talked about oxidation, we've talked about reduction, and we've talked about the definitions and what those things mean in terms of losing electrons and gaining electrons, and we've done a lot of work with that. And we've also talked about these things called half reactions, where you can take a big reaction and split it up into two smaller reactions that explicitly shows which electrons are being gained and which electrons are being lost, and that is a good way to help us figure out what is being oxidized and what is being reduced, because we can see those electrons being gained and lost in the half reactions. So we're kind of building our understanding up a little bit each time. Now we're going to talk about the concept of oxidation numbers. Now the big picture for what an oxidation number is useful for, big picture, is it basically lets us track electron transfer in a chemical reaction. And because it lets us track electron transfer, it basically is a way for us to tell what's being oxidized and what's being reduced in a reaction. So again, we've done a lot of this stuff before with the half reactions. We busted the reaction up into two pieces, looking at the electrons being gained and lost, and that tells us what's being oxidized and what's being reduced. The oxidation numbers is a way to get the same information. It lets us track the electron transfer, and it lets us figure out what's being oxidized and what's being reduced, but we don't have to write any half reactions on our paper. So we can have one big reaction written on a piece of paper, we can assign oxidation numbers to everything in that reaction, and just by looking at the numbers we can figure out basically what's being oxidized and what's being reduced. So the big picture roadmap for this section is, I'm going to explain what an oxidation number is to you briefly, and then what we're going to do is write there's a little bit of a process to find the oxidation number. It's not hard, but I need to write some rules down on the board. All right, and then once I get them on the board, then what we will do is turn our attention to just doing a lot of problems. We're assigning oxidation numbers to lots and lots of different elements and compounds. So an oxidation number is a number that you assign to the elements in a compound or to the elements in a polyatomic ion or some assemblage of atoms and elements like that. It's a number that you assign to those pieces there that basically represents the charge that's held by that piece. So if you have sodium chloride, there's two things in there. There's sodium and there's chlorine. So we can assign an oxidation number to sodium and we can assign an oxidation number to chlorine. And it's basically representing the charge that's held onto by those two things that make up sodium chloride. And what we do is we assign those oxidation numbers to everything in the chemical reaction, and then by looking at the numbers we can go and figure out basically what's being oxidized and what's being reduced. All right, that's basically what an oxidation number is. Now I want to stress something that's very important for you to understand before we actually learn how to assign oxidation numbers to everything in the reaction. And you'll probably read this in your book and your teacher will probably mention it to you, so I want to say a couple of words about it. These oxidation numbers, in many cases, in many elements in the compounds that you're dealing with, represent the actual charge that we think that those particular atoms have in the compound. All right, so you know, a lot of times, for instance, oxygen likes to have a -2 charge, so we'll say that its oxidation number is -2. But it's important for you to realize in the definition of oxidation number that it's really just a bookkeeping method. It's a bookkeeping method. So sometimes the oxidation number is going to be reflected in the actual charge, what we think this thing is actually charged to. But in some cases, depending on the compound you're looking at, the oxidation number that we give it isn't really going to line up with what we think that charge might be. So sometimes it's kind of a fictitious bookkeeping method. So what we're going to do is we're going to write down the method, and there's several steps that you've got to go through in priority order to put the oxidation number down on paper. And you follow those steps to the letter, and the number that you get for the oxidation number, just keep in mind that in most cases it represents the charge on that item, but it's fictitious bookkeeping in order for us to track the electron transfer in the reaction. So just keep that in mind, that in most cases it's a real charge, but sometimes it's fictitious, it's hypothetical, it's not really reflective of what's really going on in there. But what we care about in the end, in a little bit, is the change in the oxidation number. From one side of the arrow in the reaction to the other side, we're going to be looking at the changes in the number. So the change in the oxidation number is really what we're mostly caring about, not really the actual value of the oxidation number too much itself. So keep that in the back of your mind. So rather than continue to talk about this, let's go ahead and put something down that you can sink your teeth into and try to understand in terms of oxidation number. So let's take something simple. Let's look at something that I know you've seen. So sodium chloride, sodium and chlorine, okay? One atom of each, okay, ionic compound. What do you think, looking at the periodic table, what do you think the charges on these two guys would be? Well, if you look at chlorine, it is in the column right next to the noble gases. So chlorine always wants to have a charge of -1, if possible. All right? And sodium always wants to have a charge of +1, if possible. Okay? So these guys, +1 for sodium and -1 for chlorine, we call these oxidation numbers. So I told you a minute ago that it represents, in general, you can think of it as the charge on these guys. So this is the oxidation number. The oxidation number of chlorine would be -1. The oxidation number of sodium would be +1. Okay, let's look at another one real quick. Calcium chloride. All right, so again, chlorine almost always really wants to be a charge of -1. And so calcium here, always, if you look at the periodic table, it's in the second column from the left-hand side. It always wants to lose 2 electrons, so it always wants to have a charge of +2. So these would be the oxidation numbers. This is the oxidation number of calcium, it's +2. The oxidation number of chlorine is -1. Now notice a couple things that are important things for you to note, is that in the sodium chloride compound here, we have +1 and -1, and we have subscripts of 1 there. So if you add up the oxidation numbers in that compound for all the atoms, 1 atom of sodium and 1 atom of chlorine, for the chloride, right? Then you have +1, -1, then the sum of those things is 0, okay? Now also look at calcium chloride. Here we have 2 chlorine atoms, so 2 times -1 would give us -2. If you add up all the oxidation numbers of all the chlorines, you're going to get -2. Calcium is +2, so +2 and -2 also give us 0. So what we're going to find out in a minute when I write all the rules of the oxidation numbers down is that's an important observation that's always true. In a neutral compound, like these are neutral compounds, right? The sum of the oxidation numbers of everything in there, when you take into account the subscripts and everything, has got to be 0. And that's something we learned kind of early on. We didn't call it oxidation numbers, but back when we learned how to put the charges up here and do the crisscross thing to get the subscripts, basically that's what that's doing. That process is ensuring that the compound that you end up with is going to have a 0 charge. All right, so these are oxidation numbers. Nothing too fancy, nothing too complicated. You might wonder, why are we even learning this? We already know how to do these. But what's going to happen is when you have more complicated compounds, how do you know what's going to take priority? Is the oxygen going to have -2? Is the hydrogen going to have +1? Sometimes when you just look at the periodic table at face value, you're going to get oxidation numbers that aren't right unless you follow the specific rules that we're going to lay out in a second. So for these simple 2-element compounds like this that are real simple, that are things we do a lot, it's pretty much going to be the charge that you read right off the periodic table just because it's that way. But there's a priority pecking order to writing down these guys that we need to learn. One more thing I want to tell you before we actually show you what that deal is, and this is kind of an aside that I want to make sure and point out to you. Okay, for oxidation numbers, it's kind of a convention that you write it like this: -2, +3, -4, whatever. You put the sign and then you put the number. So it's +3, -4, -2, whatever. Okay, back from before when we did the charge, we typically like to write that as 2 plus, 3, -5 plus, whatever. So when you're talking about the physical charge on an object, typically you put the number and then the sign after, the number and the sign. Sometimes I've been consistent with that, sometimes I haven't, but that is really what you should strive for, and in your book it's probably going to have it written that way. So if you see a plus after, it's implying that that's the actual charge. Whenever you see a sign and then the number after, it's implying that it's talking about an oxidation number. Now, I'm trying to reiterate this a lot because it's a common question that people have. These oxidation numbers, in many, many cases, are going to end up being the actual charge that we've been using on the periodic table all this time. So in most cases, you're going to look at them and it's not going to matter because the charge on the thing and the oxidation number are basically going to be the same thing. But I'm going to work a couple problems here in a minute that I'm going to show you that the oxidation number that you can get isn't really going to be lining up with what we think it should be, because the oxidation number is basically a bookkeeping method. It's a set of rules that we use to assign oxidation numbers to things, and the only thing we really care about is who changes, who increases their oxidation number and who decreases their oxidation number. So that's what we're looking for in reactions, and that information can tell us what's being oxidized and what's being reduced. All right, so I don't want to get too far ahead of myself. What I want to do now is erase this little introduction off the board, and then I will write down the rules of finding the oxidation number. There's not too many rules. There's 6 rules. They're very easy to understand. Let me get them on the board with you step by step, and then we'll work a lot of problems and give you a lot of practical practice with finding these oxidation numbers. Hello and welcome to this section of the chemistry tutor. In the last section, what we did is just introduce the concept of an oxidation number. We said it's a bookkeeping method to track electron transfer in a reaction. We gave a couple of very simple problems just showing you how finding the charge on the items in a compound basically is what we're calling the oxidation number, and I was very careful to stress that in some cases it's not going to make a line up with what you think the answer should be, and that there's a method for finding these oxidation numbers. So what I'm going to do now is start with a clean board and write down the method. It's not very hard, but you do need to follow it in priority order. So what I'm going to do is write down all 6 little rules that you follow for finding the oxidation number. It's very important for you to realize that when you get done with it, there's going to be 6 rules. There'll be 1, 2, 3, 4, 5, and 6. So when you're finding your oxidation numbers, you're going to start at rule 1, and everything at the top of the list is going to overrule any rule underneath it. So the way you go through when you're looking at your compounds is when you start from rule 1 and you march down the list, and everything that you find that applies, you go ahead and do that. So if something is at the top of the list, it takes priority over something that's at the bottom of the list, because sometimes you might have conflicting ideas about what to do. So this is very easy once you get the hang of it. Okay, so the very first rule, rule number 1, is something we've actually talked about before, and so here we go. There's a part A and a part B, so let's call it 1A. For atoms in a neutral atom, molecule, etc., the total of all oxidation, I'm going to do oxid for oxidation, numbers, is 0. All right, I actually mentioned that to you a minute ago when we did sodium chloride. I said, hey, when you add these things up, the oxidation numbers, when you sum them up, is 0, and that's all that this is saying. So as an example, if you have the atom just sitting off by itself, the atom iron, Fe, what it's basically saying is that you know by definition, since it's sitting by itself, the sum of the oxidation numbers of everything in here, which is just one atom, has got to be equal 0. So since you know that the sum of the oxidation numbers have to be 0, then it tells you that if iron is sitting by itself, neutral atom, by itself, the oxidation number of this must be 0. All right? If you have hydrogen gas just sitting off by itself, floating in a balloon or something, you know that the sum of the oxidation numbers in this molecule here is 0, because it says for atoms in neutral atoms, molecules, etc., any kind of compound, anything, the total of all the oxidation numbers has to be 0. So that means that since the sum of these oxidation numbers are 0, it's basically implying, and since it's the same atom in there, it's basically implying that the oxidation number of this hydrogen is 0. All right, let's look at something like magnesium bromide, MgBr2. What it's saying is the sum of the oxidation numbers in this compound is 0. So if I find the oxidation number of the magnesium, and if I find the oxidation number of the bromine, then once I multiply by the subscripts and add everything together, I'm going to get 0. So all Rule 1A says is something that you already really kind of know from what we talked about before. The sum of all the oxidation numbers in a neutral atom or compound always has to be 0. All right, that's all that this is saying. And it's an important rule, and it's the very first rule on the list. Now 1b is very similar. That's why they wrap it up in the same rule. In an ion, right, the sum of the oxidation numbers is equal to the charge on the ion. The best way to illustrate this is by example. It makes a lot of sense whenever you look at it. Let's say I have the ion PO4, and this ion has a charge of -3. Notice that when I write 3 negative like this, the sign of this guy is written after the number, so that means this is the charge on this whole ion, right? So this whole ion has a charge of -3 when you kind of sum it all together. And that means here that the sum, this little sigma here means sum, it means you add everything together. The sum of the oxidation numbers has got to be equal to -3. So if I find the oxidation number of this guy, and if I find the oxidation number of this oxygen here, and then if I multiply by the subscripts and add all the oxidation numbers of everything in here, it's going to equal -3, right? And it's the same kind of rule as what's going on here. The charge on these things are always 0. So the sum of the oxidation numbers really is equal to the charge here too. It's just always 0. So anytime you have a charged thing like an ion, the sum of the oxidation numbers is equal to that. What about NH4, the ammonium ion? All right. So again, the sum of the oxidation numbers, in this case, is going to equal +1. Because the total charge of this whole ion is +1, so the sum of the oxidation numbers are going to be that. What about a chromium ion? A single atom that has a charge of +3, right? So that means the sum of the oxidation numbers is going to equal +3. So this is rule number 1. Very simple rule to understand based on what we've talked about before, but very important for you to understand. When we have neutral atoms, neutral molecules, the sum of the oxidation numbers of all the little oxidation numbers in there have got to add up to equal to 0. When we have charged objects like ions, the sum of those oxidation numbers have to add up to the total charge on that ion. All right? So that's rule number 1. And that basically applies to everything, because everything in nature is either going to be a neutral atom or molecule, in which case the oxidation numbers will sum to 0, or it's going to be an ion of some kind, in which case the oxidation numbers are going to sum to give you the charge on that ion. So everything's going to fall into one of those two categories, and that's why it's rule number 1. It applies to basically everything. It's the top of the food chain, always going to apply. Now let's go and look at rule number 2. Okay, so going down the list. Here's where we start assigning oxidation number. In compounds, group 1A metals have oxidation numbers of +1. What this means is group 1A, that's the very first column in the periodic table, the one with hydrogen in it. All of those guys have oxidation number of +1. Notice this is what you would expect. When you look at the periodic table, I already told you how to read the charges, kind of like the charge that it's going to want to have. The very first column, the one that hydrogen is and all those things, they always want to be +1. So this is just affirming that. It's very high up the list. It's telling you that these things, these metals over there, they're extremely predictable. They all want to have a charge of +1, which means they all want to have an oxidation number of +1. Group 2A metals have oxidation numbers of +2. Okay, so that's the column that's right next to the first one. So the first column wants to have charge +1. Second column, the one right next door, wants to always have a charge of +2. And again, we've been using this fact over and over, but we're just kind of putting it on the board in a priority order, showing you this is very high up the food chain. These guys are extremely predictable. So they're going to be something that we're going to see all the time. So let's give an example. What if I have sodium SO4, okay, Na2SO4. What this is saying is when I look at this guy, I'm going in priority order, right, if I were to look at it. So what it's telling me is this is a neutral compound, Na2SO4. It's not an ion, so the sum of all these oxidation numbers is going to be equal to 0. That's the rule number 1. But then I come to rule 2 and I see that, the guy applies here because sodium is in group 1A. So what I can tell is that Na has oxidation number of +1. I know that right away because it's rule number 2. All right? What if I had something like calcium PO4? All right? Again, calcium's wrapped up in here. I don't have anything on this list about phosphorus or oxygen yet at all. But I know that calcium is on this list. It's in group 2A, so that means that calcium, the oxidation number, is +2. All right? So I haven't given you rules to find the other ones yet, but what I'm trying to tell you is that you follow a priority order. You look and you see first, okay, do I have any group 1A or 2A elements in this guy? And if I do, I know what those oxidation numbers are. And then I'm going to have a rule 3 and 4, and you just keep marching down the list until you've assigned a number to everything in whatever it is you're looking at. All right? Let's go to rule number 3. Rule number 3. In compounds, fluorine F oxidation number is -1. That's important enough that it goes off by itself. Fluorine is always going to have a -1. So for instance, if you have a compound HF, then fluorine, you know right away, is -1. All right, so again, we look at this guy, HF, we see the F here, and we see that it's right here, it's always -1, so we know right away without doing anything else that the oxidation number is -1 for that guy. All right, so let's look at step 4, or in rule number 4. In compounds, the element hydrogen has oxidation number is equal to +1. Okay, so if you think about that, that makes sense, because if you look at hydrogen on the periodic table, hydrogen is in that first column, and it usually does like to have a charge of +1, right? So let's give another example. HCl, hydrochloric acid, right? So we know without looking that the hydrogen in here, okay, has an oxidation number of +1. Okay, oxidation number of +1. Now again, I know you don't really see it yet until we work the problems, but you know this is a priority list. So for instance, we haven't talked at all about chlorine yet, so we don't know anything about what's going on with chlorine yet, but we know hydrogen is going to give us this. We have rules that talk about the group 1A metals and the group 2A metals like sodium and calcium and you know, things like that. And we have rules that talk about certain things like out of place, like why would fluorine be listed as a separate rule? That's because it's a little bit higher up the priority chain. Fluorine always wants to have, or almost always wants to have a -1, so it's up there. So things that are lower on the list, you may not actually get to whenever you're doing your calculation of the oxidation number, because you may find the answer to all of the elements in there without having to get to the bottom of the list. So I guess it just needs to show you by a few problems what I'm talking about, but just keep in mind this is a priority list. The things at the top of the list are the kind of the surefire things. The thing at the bottom of the list, you may not even get to them because you know you may solve the problem before you get down there. So let's look at 5. Okay, in most compounds, oxygen has oxidation number -2. And again, this is something that you've seen before. Oxygen is over in that column toward the right by the noble gases, but it's 2 columns over, so it usually likes to have a -2. But again, this rule is down farther on the list. So even though it says in most compounds oxygen has an oxidation number of -2, depending on the compound you have, oxygen may not have an oxidation number of -2 if you get through all of these rules that are up above it, and it dictates that hydrogen is something a little bit different than -2. So you just go through the list in priority order, but don't get the idea that just because it says -2 here, oxygen is always going to have -2, or just because it says hydrogen is +1, that it's always going to be +1. Though that's not true. This is a priority list. So when you're going down there, if you calculate that that hydrogen has an oxidation number different than this because of rules that are above this, then that's just going to be the answer. So this is a priority list. Just keep that in mind. Let me go ahead and show you an example here with the oxygen. Carbon monoxide. Oxygen is going to be equal to -2, an oxidation number. -2. Okay? All right, let me put one more thing, see if I can squeeze it in. 6. Okay? In 2-element compounds with metals, comma, group 7A, in 2-element compounds with metals, group 7A elements, those are the ones nearest the noble gases, they have oxidation number of -1. Okay. Group 6A metals have oxidation of -2, and group 5A guys have elements have oxidation number -3. So let me give you an example, okay? So, or a quick example. Group 7A, that's the column right near the noble gases. So those are things like fluorine, chlorine, bromine, ... All right. Group 6A, that's not the column right next to noble gas, but the one over just to the left. That's oxygen, silicon, oxygen, sulfur, ... Okay? And the group 5A would be things like nitrogen, phosphorus, arsenic, ... All right, so this basically outlines all of the rules needed to find oxidation numbers. I know it looks like a lot, you know, we throw them on the board, but basically this is it. And so what you do is if I give you a compound and I say find the oxidation numbers of everything in this compound, then what you would do is you would start with rule 1 and you would figure out, okay, is it neutral or is it not? And you would assign the rule here. And then you would go to rule number 2 and you would figure out, okay, do I have any group 1A metals or 2A metals? If so, I assign those oxidation numbers. And then you would say, okay, look down here and you would say, okay, do I have fluorine in there? If I do, I assign that a -1. Then you would say, okay, do I have any hydrogen? And I would assign +1. Then you would say, okay, do I have any oxygen? And if I do, I would have -2. And then I would say, all right, do I have any group 7, 6, or 5? And is these 2-element compounds? And then if so, I would assign -1, -2, -3. But what I'm trying to say is that as you do problems, you'll figure out that you might not get all the way to the end of this list. You might complete the problem up here in rule number 3 or 4 and have all the oxidation numbers for everything you need. So there's no point in talking about it anymore. We need to do some problems. But before we do that, I need to give you a couple of exceptions. Okay? With all rules of all kinds, there's always exceptions. All right? So let me give you a couple of exceptions because you're probably going to run into them and then you're going to scream and say, well, why didn't it follow these rules? Okay? So this is an exception to rule number 4. Rule number 4 is the one that talks about hydrogen, saying the oxidation number in compounds with hydrogen is positive 1. Okay? If hydrogen is bonded to a metal, okay, to a metal, then the hydrogen oxidation number is actually -1. So notice what this rule said. It said in compounds, hydrogen's oxidation number is +1. So you would take that to the bank and you would assign +1. However, there's an exception. If hydrogen is bonded to a metal, okay, then the oxidation number is -1. Now, what could that be? Let's say you have some weird thing, some weird looking thing like NaH, which, believe it or not, is possible, or CaH2, calcium hydride, or something like that. All right. So in both of these cases, you have the hydrogen bonded to a metal. All right. So the hydrogen oxidation number is -1. All right. That's an exception because that's kind of rare. You don't see that too much. When you see hydrogen in compounds, it's not bonded to a metal most of the time. Think about it. Water is H2O. That's bonded to a nonmetal, right? Hydrogen is bonded to a nonmetal. What about hydrogen sulfide? That's a nonmetal. What about hydrochloric acid? HCl, right? So most of the time, hydrogen's bonded to things on the right-hand side of the periodic table, and in all those cases, the oxidation number of that hydrogen is going to be +1. But in the crazy cases when you have metal hydrides, where you have like a sodium hydride or calcium hydride or something like that, that's weird when it's bonded to a metal. In that case, the oxidation number of hydrogen is -1. So we put it as a footnote because it's not very common, but you need to know about it. Okay? Only one more exception, then we're done. Exception to rule number 5. Which rule number 5 is dealing with most compounds, oxygen has oxidation number -2. Okay? When oxygen atoms are bonded to one another, okay, then things are a little bit different. So for instance, you have this thing called peroxides. Let me just go ahead and put it like this, peroxides. You've heard of hydrogen peroxide, right? So peroxide. For instance, H2O2, this is hydrogen peroxide you find in your medicine cabinet, right? In this case, the oxidation number of oxygen is equal to -1. So if you follow the rule blindly, it says most compounds, oxygen has an oxidation number of -2. But we're giving you an exception to that. We're saying, okay, when oxygen atoms are bonded to themselves, so here you have H2O2, you have 2 oxygen atoms, attached inside of another compound. In that case, the oxidation number is going to end up being +1. All right, so here we have all of the rules needed to figure out the oxidation number of elements and atoms in a compound or an ion. So what we're going to do in the next section is we're going to use these rules in priority order to go and figure out the oxidation number. And don't forget the big picture. Why do we go through all this trouble? The reason is because when I have a chemical reaction laid out, I want to be able to assign an oxidation number to every single atom and every single compound in that reaction. And once you get the hang of it, it's very fast. It takes you just a few seconds. And then I'm going to look at the changes in the oxidation numbers on the left-hand and on the right-hand side of the arrow in the equation. I'm going to figure out what is increasing their oxidation number and what is decreasing their oxidation number. And that's going to tell me what's being oxidized and what's being reduced. And that's why we're doing this. We're trying to track electron transfer to figure out what's being oxidized and what's being reduced. So again, real rapidly, rule number 1 says that if you have a neutral compound, the sum of the oxidation numbers of everything there has got to be 0. If you have a charged ion, the sum of the oxidation numbers is going to be equal to the charge. Rule number 2 is if I have a column 1A or column 2A metal, then the oxidation number is +1, +2. That's very high up on the list. Fluorine is always going to have an oxidation number of -1. Hydrogen is always going to have an oxidation number of +1 unless it's actually bonded to a metal, in which case it'll have a -1. Okay? And then we have oxygen. Oxygen is going to have an oxidation number of -2 unless Oxygen is bonded to itself like in a peroxide, and then the oxidation number is -1. And then finally, in two-element compounds with metals, the things on the right-hand side of the periodic table, column 7, 6, and 5, are going to behave like you would expect. The column 7 guys are going to have charge -1. The column 6 guys are going to have charge -2. The column 5 guys are going to have charge -3. That's what we've actually learned a long time ago. But notice that this is at the very bottom of the list. So as I work problems, you'll see that sometimes the answers you get for some of these are not quite what we expect, because this is a priority list. If I get all the oxidation numbers after I get to this step, then nothing below it even matters. And so that's something you have to keep in mind. So let's go and wrap this section up. Go on, follow me to the next section, where we'll finally put some compounds down and give you some real practice with finding these oxidation numbers in compounds and ions. Hello, and welcome to this section of the Chemistry Tutor. We've done a lot of groundwork here in the last couple of sections talking about what an oxidation number is and the rules for finding oxidation numbers. But really, until you get to this section right here that we're in, so that you can actually apply all of these rules, you really can't get a great appreciation for how to do it. So we just need to dive in and work a lot of problems, and that's exactly what we're going to do. It's very important to be able to know how to do these oxidation numbers right, so that you can actually use it for your chemical reactions and figuring out what's being oxidized and reduced later on. If you don't have a good grounding in this, then follow-on topics are going to be tough, even when they're not hard. So what I've done is I've left all the rules on the board. Everything is still here. I haven't really erased anything. Everything's still here. And what I'm going to do is work on the right-hand side for all the problems, so that what we can do is refer back to the rules that we've already used. So you don't need to write anything down as far as rules. I've got them all on the board. And they're in your books. You might want to jot them down at some point, but as far as working these problems, I've already got them on the board. So let's jump in. I think you'll be surprised at how some of this stuff ends up working out. So let's do problem number 1. We have a potassium ClO4. Okay, so this is a compound. We've got potassium atoms in there, we've got chlorine atoms in there, and we've got oxygen atoms in there. And so, if you just look at it, if you look at the periodic table, you're going to say to yourself, okay, well, potassium likes to have charge of +1, chlorine likes to have a charge of -1, and oxygen likes to have a charge of -2. That's what we would typically say from everything we've learned up until this point. Some of those answers are going to be right, but one of them is not going to be right. So if you just go from your gut instinct, what you think should be, you're going to be wrong a lot of times. You have to use the method that we've outlined here. So the very first thing we do is we go and we look at the priority order. Rule number 1 says for atoms in neutral molecules or whatever, the sum of the oxidation numbers has to be 0. And rule number 1 applies here. In fact, rule number 1 is always going to apply because we're almost always going to have neutral atoms here. So the way that I want to put this down is I want to put an asterisk here, just to kind of remind myself. What I'm going to say is that the sum of the oxidation numbers is going to be equal to 0. And in parentheses, I'm going to put rule 1. This is not something you have to do, but what I'm going to do is write down what I'm doing, and I'm going to put the rule that I'm using, so that if you're on a test and the teacher sees that you know what rules you're using, then you can get some partial credit if you don't get the final answer correct. All right, so I like to do that, plus it also reminds me of what I'm doing. So I've done rule number 1, okay, and then I go down and look for rule number 2, and I see, does rule number 2 apply? Well, it says in compounds group 1A metals have oxidation number of +1. What we have here is this guy, and this guy is in column number 1, so it is a group 1A metal. All right, so I'm going to put an asterisk here, and I'm going to say that for potassium, K, the oxidation number is +1. All right, and I'm going to write down to myself rule number 2. Okay, because rule number 2 applies. All right, now the next thing you have to do is look and say, okay, do I have enough information to find all the other oxidation numbers? Well, I know the oxidation number here, and I know they all sum up to give me 0, but I don't know what chlorine is and I don't know what oxygen is, so I don't have quite enough to do the final answer. So I go down and I say, do I have any group 2A metals, right? I don't have anything like that in there, so I skip over that. Let me go to step number 3, or rule number 3. Do I have any fluorine in here? And I go over here and look and I say, I don't have any fluorine in there, so that's not a big deal. Then I go and look at number 4. Do I have any hydrogen in here? I go over here and I don't see any hydrogen, so that doesn't apply. I go down to number 5. Do I have any oxygen in here? And oxygen would be a -2. I do have oxygen in here, so I put a little asterisk and then I say the oxygen is -2, and that's rule 5. All right, so then I go back and look and see, do I have everything needed to find everything here? I know what potassium is because that was given in the rules here. I know what oxygen is. I don't know what chlorine is. So I think, okay, a lot of students will think, okay, well, I'm going to go and keep looking. So I'm going to go keep looking down here and down here. Eventually, I'm going to get down to the group 7A nonmetals, and I'm going to see that they have oxidation number -1. So I might be tempted to put for chlorine -1 here and say, okay, I've got all the oxidation numbers, but you would be wrong, okay, if you do that. Because, believe it or not, even without going to the bottom of this list, I actually have enough information here to find the answer. And the reason is because I know what potassium is, I know what oxygen is, and I know that the sum of all of these oxidation numbers in this compound have got to be equal to 0. That is critical, crucial information. So let me see if we can use this. What is the oxidation number of potassium here? We just said it was +1, so I'm going to say, okay, 1. What is the oxidation number of chlorine? I don't know what it is, so I'm going to add to it, I'm just going to put Cl there because I don't know what that oxidation number is. What is the oxidation number of oxygen? Well, it's -2, but I have 4 atoms here, so I have to say 4 atoms times -2 for each one. And all this stuff has to be equal to 0. What I am doing here is I'm applying rule number 1, which is the very first rule in all of these things. All right? So I found rule number 1. I had to use this rule. I had to use this rule. But when I get down to this point, I can write like a little tiny equation there, and I can figure out what chlorine is because the sum of these guys have to be equal to 0. So what I do is I say 1 plus Cl. 4 times -2 gives me -8 is equal to 0. And then I have Cl minus 7 is equal to 0 because -8 plus 1 gives me -7. And if I move the 7 to the other side, then chlorine is +7. So what I have found is the oxidation number of chlorine is actually +7. So the way that you write this down for your answer, or you can do it any way you want, you can circle them, I guess, but a lot of the ways that you'll see it is you'll see the compound rewritten, KClO4, and the way I like to do it is I like to draw a line from the potassium, and you just put +1 up here. Put the line from the chlorine up here, and you put +7 up here. And you put the line from the oxygen, and you say -2. So when you have lines drawn like this with plus or minus signs in front of the numbers, everyone's going to know that these are oxidation numbers, and that's what you have. So if you like, you can circle these on your paper, but this really explains and shows that you found every element's oxidation number, and here they are. And notice that the sum of these guys, the sum of these oxidation numbers, is 0. But you have to take into account how many atoms of each you have, because when we say that oxygen has an oxidation number of -2, that means that every oxygen atom in there has an oxidation number of -2. So you have to go -2 times 4. That's going to give me -8. So I'm going to have -8 from this. Here I'm going to have +8 when you add these together, and when you add all that together, you're going to get 0. So let's make sure, and let's see what's the wow factor here. We found that chlorine has an oxidation number of +7. That is nothing like what we would guess from looking at the periodic table. In the periodic table, chlorine sits way on the right-hand side, right by the noble gases. And in previous sections of this class, we've talked about that chlorine likes to have a charge of -1 because it's right next to those noble gases. In fact, we can see that down here in 2-element compounds with metals. Group 7A, which includes chlorine, likes to have a -1. But number 1, this is not a 2-element compound. Okay, this is a 3-element compound, so that doesn't apply anyway. But even if it was a 2-element compound, it didn't matter because we had enough information to find the oxidation number of everything in there before we got down to this rule. And that's what I was trying to tell you. If you just look at the elements and just try to give oxidation numbers based on just looking at the periodic table. If you don't follow the priority pecking order, you're going to get the wrong answer a lot of times, because this is just a bookkeeping method. It doesn't necessarily mean that the charge on chlorine is +7. It just means that we have a set of rules that we use to assign these numbers, and it just so happens that when we do it this way and we track before and after the reaction happens, we can see what changes, and that tells us what's been oxidized and what's been reduced. All right, so let me erase this. We'll do some more problems and give you some practice with that. But what you need to do is go and write down your rules. You're going to need to do this almost every time. So basically, you're going to be calculating the value of the last element's oxidation number by summing them up like this. So get used to dealing with that, because that's how we're going to do most of these problems. All right, let's say we have the compound K2SO4. All right, so we want to find the oxidation number of everything in here. All right, so the very first thing we do is we notice that is a neutral compound, and rule number one is always dealing with if it's neutral or if it's an ion. So if it's always neutral, rule number one means the oxidation numbers, the sum of them, are going to be equal to 0. All right, so the way I do it is I put a little asterisk here and I say the sum of the oxidation numbers is equal to 0, and that's rule 1. I'm just going to remind myself of that fact. So then I go down and look and say, okay, does rule number 2 apply? Do I have any group 1A or 2A metals? And in fact, I do have a potassium here. So what it tells me is K is +1, and that's rule 2. Basically, everything in column 1 and 2 of the periodic table is so reactive and so volatile that it's always going to want to form either a +1 or a +2 ion every time it forms. So that's why it's so high up on the list. It's very guaranteed for that to happen. So since we have a potassium, we know it wants to be +1. All right, so then we go down the list. Do I have any fluorine in this compound? No, I don't. Do I have any hydrogen in this compound? No, I don't. Do I have any oxygen in this compound? Yes, I do. And it's an oxidation number of -2. So what this tells me is oxygen is -2. And then I look and I write down this is rule 5. Okay. And then I ask myself, do I have any rules, or do I have enough information on the board to find sulfur, which is the only thing that I'm remaining, that I have remaining? And the answer is yes, I do have everything I need, because I can sum these guys up. So for potassium, it's +1 for the oxidation number, but there's 2 of them. So I say 2 times 1 plus the oxidation number of sulfur, which I don't know, plus the oxidation number of oxygen, but there's 4 of them. So I do it like this, because I have 4 atoms of oxygen, each with a -2 oxidation number. So 2 times 1 gives me 2. 4 times -2 gives me -8. And now I just add these guys. 2 plus a -8 gives me -6. And then I move the 6 to the other side, gives me +6. So the oxidation number of sulfur is +6, and that's the final answer. Now, if I wanted to write this down the way you might want to write it on your test, K2SO4, I would write it down. And then I would say, all right, draw a line. Potassium is +1, sulfur +6, and oxygen -2. And these would be the oxidation numbers. I would circle this. That illustrates everything nice and compactly, or I could just circle it on your test. Notice that if we continue going down here, the only thing on this list that talks about sulfur is this one here, where it says the oxidation number would be -2, because it's in that column 6 over there for sulfur. Obviously, the answer we got is not anywhere close to that. We got a positive number for the oxidation number of sulfur. Also notice that this is in reference to 2-element compounds with metals. So this is not a 2-element compound at all anyway. So even if we got to the bottom of the list, that rule wouldn't have applied anyway. So a lot of time, notice there's no rule here talking about copper or talking about aluminum or talking about any of those things. Basically, the oxidation number rules tell you what the most reactive things are going to want to do. The oxygens, the hydrogens, the calciums, the sodiums, and they lock it down. And then we know that because the sum of the oxidation numbers have to be equal to 0, you're always going to be able to find out what that last one is just by doing the math here. So that's kind of how you need to kind of attack these problems. Write down what you know and then use the math to find the last remaining one. All right, so let's look at another one, Al2O3. So the first thing we do, rule number one, you should know by now, talks about if it's a neutral compound, then the sum of the oxidation numbers is 0. This is a neutral compound. So first thing I'm going to say is the sum of the oxidation numbers is 0, and that's rule 1, okay? And then I go and look and say, okay, do I have any group 1A or 2A metals? I don't have any of those. Do I have any fluorine? I don't have that. Do I have any hydrogens? I don't have that. Do I have any oxygens? I do have oxygens. So I will go over here and I will say for oxygen is -2, and that's rule 5. So then the first thing you do is you say, oh, do I have enough information to find the answer to aluminum, which is the only other thing I have? And the answer is yes. I don't need to keep going down the list because I already have enough information to find all remaining oxidation numbers. And like I said, I'm trying to get you to understand that the very last thing you're almost always going to do is use the math here. So I have 2 aluminums. So I'm going to say 2 aluminums, right? I have to keep track of the number of aluminums I have, plus 3 oxygens, each with a -2 oxidation number, and they have to sum to 0. I'm using both of these rules to write the simple little equation here. So 2Al minus 6 is equal to 0. And then I move to solve for Al, I move 6 over here. 2Al is equal to 6. And then to get aluminum by itself, I divide by 2. So Al is equal to 3, positive 3. And that is the answer there. So that's the oxidation number of aluminum in this compound. So if I do Al2O3 and I want to represent it, typically how you might do it on tests, for the aluminum, it would be positive 3, and for the oxygen, it would be -2. And that would be the way that you'd probably end up writing that. Now, this little equation thing is probably the most algebra that you'll see in a chemistry class, but it's a great example of how you might actually use algebra for something besides algebra class, right? So you're writing a little equation. You know the sum of the oxidation numbers have to be 0, and you're literally writing it out. 2 times whatever this is plus 3 times -2 has got to be equal to 0. We're moving this over, and then we're dividing by 2. If that kind of math, the math of solving that simple equation seems foreign to you, then go back and get my algebra materials to refresh your memory on how to solve simple equations like that. But that's what we're doing here. All right, for the next problem, it's a little bit different. Very simple. I just want to point it out to you. What if you have the compound P4? So 4 atoms of phosphorus bound together, and I ask you, what is the oxidation number of phosphorus here? Well, it's very simple actually, because this is a neutral compound, right? 4 atoms of phosphorus, there's no charge anywhere, so it's neutral. So you know that the sum of the oxidation numbers have to be equal to 0. And because you have 4 identical things bound together, they're all going to have the same oxidation number. The only way that this can have oxidation numbers that all add up to 0 is if the oxidation number of phosphorus is 0. So the way you would write it down is you would say P4, the oxidation number of this is 0. And this is what you're going to see all the time when you have atoms off by themselves, or little molecules that have the same atoms, like hydrogen gas we talked about, H2. The oxidation number of that was 0 as well, because the sum of the oxidation number of all of these phosphorus atoms have to be 0. And so that you add them up, the only way it's going to happen is if the oxidation number of the phosphorus atom is 0. So when you see something off by itself, like an iron atom or an H2 or Cl2, chlorine gas, or something by itself, and it's neutral and it's over there by itself, the oxidation number is basically going to be 0 for that element. All right, the last problem we're going to do in this section is going to be Na2O2. Na2O2. Okay, and so what I'm going to do is go in priority order down the list. So this is a neutral atom. There's no charge on it, or it's not an ion or anything. So the sum of the oxidation numbers is equal to 0. Sum of the oxidation number is equal to 0. All right, so then let's go down the list. Okay, do I have any group 1A metals? And the answer is I do. I have a lot of sodium here. So the sodium is +1. All right. And then the question is, you always have to circle back every time you write something down. Do I have enough information to find the answer to all of these things? To find the answer to all of these elements? And I do. I don't have to even look at this anymore. I don't need to do anything else because I've got enough information. So the way you do it is you say 2 times the sodium plus 2 times oxygen, whatever it is equal to 0. Okay? And actually, just to make this clear, instead of 2, 0, it looks like 2 times 2, 20 because of the 0 there. I'm going to put oxygen. 2 times the oxygen is equal to 0. So this is going to be 2 plus 2 times whatever oxygen is. And then I move this over here, so I'm going to have 2 times the oxygen, negative 2. I move that over there. And then to get oxygen by itself, I divide by 2. So I get negative 2 divided by 2, and I'm going to get negative 1. So the oxidation number of that oxygen in there is negative 1. All right? So if you wanted to write that down, Na2O2, what we have found is the oxidation number of the sodium is plus 1, and the oxidation number of the oxygen is negative 1. And that is the answer. Those are the oxidation numbers. A couple things I want to point out about this while we're here talking about it. We didn't really need to go down the list anymore because once I had, it's only 2 elements here. I mean, there's subscripts, but there's only 2 different elements. So once I know that the sum is equal to 0, and once I lock down any of these in here, then I can use math to calculate the final one. I get an answer that's negative 1. Notice that if you look at the periodic table, most of the time oxygen wants to actually be negative 2. But notice that there's 2 things going on here. Notice that number 1, we didn't even need to get down here because we had enough information to solve this problem ahead of time. So the before we got down to that. So that's what I'm saying. It's a priority list. You have to try to solve everything as early as you can, and those are going to be the answers. And if it conflicts with something down below, that's okay because it's a priority list. The things at the top of the list matter more than the things that are at the bottom of the list. And you can see that in action here. So it's not negative 2, it's actually negative 1. And on top of that, the exception to number 5, if you remember the exception for oxygen, we said there's an exception anyway. When oxygen's bonded to itself, then the oxidation number is negative 1. And the compound we had, oxygen was bonded to itself. So it makes sense that the oxidation number is actually equal to negative 1. So we solved it the right way. We shouldn't go down there and see the exception and assign the number and be done. What we should do is write down the sum is going to be 0, write down sodium, and then calculate the answer. But I'm just pointing out that it's consistent. The answer we got is actually consistent with the other rule that was also on the list that was actually a little bit lower priority. Sometimes it'll work out where it agrees, and sometimes, like we've seen in previous problems, the answer that you calculate is totally different than what the list might imply. So it's very important when we do these examples that you're learning how to go in this priority fashion. And almost always, you're going to use Rule 1 to find the last unknown element by math rather than by just looking it up somewhere. That's almost always the way it's going to be. All right, and that's why we're learning these things, so you can get the hang of that, get the practice with that. So in this section, we've learned to actually use our method to calculate these oxidation numbers. We're going to get some more practice with it in the next section, and then we're going to use it in chemical reactions to figure out what's being oxidized and what's being reduced, which is really important. That's kind of the whole point of learning this in the first place. Hello, and welcome to this section of the Chemistry Tutor, where we're going to continue working on oxidation numbers, trying to calculate the oxidation number of elements in a compound or in a polyatomic ion. And this will be the last section of problems where we are just getting the skills with the practice to find the oxidation numbers. In subsequent sections, we'll use that information in a chemical reaction to figure out what's happening with the electrons and what's being oxidized and what's being reduced. So oxidation numbers are crucial, and we've mentioned that several times already. So in this section, we've got a couple of problems. Both of them are nice to give you extra practice, and especially the second problem is going to open your eyes a little bit to one of the interesting things about oxidation numbers. So let's just jump right in and make sure you can understand these problems and also make sure that you can do them yourself. So here we have hydrogen, arsenic, oxygen, and this is an ion where the charge on this whole guy is -2. So again, we go off and we look at rule number 1, which we've done many times, And basically it says if it's an ion, then the sum of the oxidation numbers is equal to the charge on that ion. So that's what we're doing right here. And so then we go off and we write down rule number 1, the sum of the oxidation numbers is going to be equal in this case to -2 because this ion has a charge of -2. So that's the first thing. Now we go down our list in priority order and figure out first, do we have any group 1 or group 2 metals? Well, here we have hydrogen, arsenic, and oxygen. So you don't count hydrogen as a metal. Even though it's in the group 1, it's still not really considered a metal. We've learned before that hydrogen has its own rule down a little bit farther, and it also has an exception if hydrogen is bonded to a metal in a two-element compound. But bottom line is, when you look at rule number 1, you're talking about everything other than hydrogen in columns 1 and 2. So this doesn't apply. We don't have any sodiums or calciums or potassiums or anything like that. So we go down to rule 3. Do we have any fluorines? We don't have any fluorines. So we're done with that. We don't have that. Now we go and we see we do have a hydrogen. The oxidation number of this guy is +1. The exception does not apply because it says when hydrogen is bonded to a metal, such as something like this, this is quite different because this is a 3-element compound. It's really an ion. It doesn't fit into that exception, so we're going to go with the basic rule that just says that hydrogen is going to have +1 oxidation number. So what we'll put down here is we'll say hydrogen is going to equal to +1, and that's rule 4. And the top is rule 1. Okay, so then we go down to rule 5. Do we have any oxygens? Of course we do have oxygens, and so that means that oxygen is going to be -2. Doesn't have the exception where hydrogen's bonded to itself, like hydrogen peroxide, doesn't apply here. So this will be rule 5. So again, at every step of the way, you look and see, can you solve the problem? If you cover this up, you don't have enough information with the top 2 rules to cover it because you have 3 elements here. But once you lock down the second element's oxidation number, then using that along with the top guy does give you enough information, so you don't even need to look at your list anymore. So you go over here and you add up these oxidation numbers, and you have 1 plus whatever arsenic is, I don't know what it is, plus 4 oxygens. Each oxygen has an oxidation number of -2, and all of this stuff has to sum to -2 because this is an ion. So then we just continue to drag everything along. Here we have -8 from this multiplication. We have -2 here. Then we add these up. Arsenic -7 is -2. And then we move this 7 to the other side, so we see the arsenic is +5, because when you move it, it becomes a +7 minus 2 will give you a 5. And so this is the answer for arsenic. So if we want to write it on our paper like we might do it on a test, you might write it like this. So there is the ion. The negative sign is written after the number. That implies that that's a charge there that we're writing. And then we draw a little bar for hydrogen, +1. Notice the plus sign's in front of the number. For arsenic, it's +5. And for oxygen, it's -2. So it's implying, I'm using color also, but even if it's just your pencil, it's implying with the signs in the front that these are oxidation numbers. This thing here is the charge on the whole polyatomic ion that we have. So +1 for hydrogen, +5 for arsenic, -2 for oxygen. The sum of all these oxidation numbers along with the number of atoms we have is going to give you -2 because that's the charge on the ion. All right, so that's what we have right there. This is a good problem for you to learn. We've done a lot of them like this with 3 elements. Basically, you go down the list, and at each step you ask yourself, do I have enough information to find the rest of the oxidation numbers? And when you do, you calculate it and you just stop. Now the next problem is pretty interesting, and I'm doing this on purpose to show you something that I think you've kind of understand by seeing a lot of problems, but here we'll drive it home. What I want to find the oxidation number, okay, I want to find the oxidation number of chlorine in the following molecules: Cl2, Cl2O, Cl2O3, Cl2O7, and Cl2O5. So as you can see, we have lots of different compounds or molecules. This is chlorine just bonded to itself. Here's 2 chlorines with a single oxygen. Here's 2 chlorines with 3 oxygens. Here's 2 chlorines with 7 oxygens. Here's 2 chlorines with 5 oxygens. So what we're going to do is use our rules, okay? And what I want to do is I want to list what is the oxidation number of chlorine in each one of these molecules here. And what we're going to find, I'll just kind of give you the punchline ahead of time, is that the oxidation number that we find for all of these different chlorines here, they're all going to be different, okay? That's one thing that you got to try to wrap your brain around with oxidation numbers. It's because we're following these rules. And it's sometimes the way the math works out, you're going to get, see, a lot of students think, okay, chlorine is going to have the same oxidation number everywhere. Fluorine is going to have the same oxidation number everywhere, but things can be different depending on how, you actually follow the rules. So let's go ahead and see that in action. What we're going to do is we'll do this a little bit rapid fire, but not too fast. So here we have Cl2, all right? This is just 2 chlorine atoms bonded together. So we know that because of this, rule number 1 is going to come into play. And what is rule number 1? The first thing we do, the sum of the oxidation numbers is equal to 0. So this means that, that since the sum of the oxidation numbers for both of these chlorine atoms is 0 and it's off by itself, then that means that for chlorine here, the oxidation number is going to be 0 here. All right? The oxidation number is going to be 0 because there's 2 chlorine atoms. 0 plus 0 gives us 0. So anytime you have some molecule sitting off by itself, or it's like a diatomic where it's bonded to itself, like H2 or Cl2 or anything like that, and you know the sum of the oxidation numbers of all those atoms have got to be 0, the only way that can happen is if the oxidation number of the atom itself is 0. So anytime you have an iron by itself, or a nitrogen by itself, or an oxygen off by itself, anything by itself, the oxidation number is going to be 0. It's sort of the bottom line rule. All right, so let's go and take a stab at the next one. Let's do B, Cl2O. Now we're going to follow our rules, just like we always have, but we're going to kind of speed things up just a little bit because we've done so many of these problems. You know the sum of these oxidation numbers have to be 0, okay? And you know that there's no group 1A metals there, and you know that there's no fluorines there, and you know that there's no hydrogens there, but you know that oxygen is in every one of these compounds. So every one of these compounds, oxygen is going to be -2. And in every one of these compounds, once you know that oxygen is -2, then you can calculate the oxidation number of chlorine, because you know that in every one of these compounds, when you sum up the oxidation numbers, they always have to be 0. So the way we're going to pull this off a little bit faster is we'll say 2 times chlorine plus -2 for the oxygen that's here. We know it's -2. It's got to equal 0. We're following the rules. It's just I'm not writing everything out because we've done so many problems. So you say 2 times Cl, move the -2 over, and you get +2. So Cl is +1 here. So I'm going to circle that. Now notice right away, I'm going to go ahead and write it in the compound Cl2O, the molecule Cl2O, and then I'll say in Cl2. So just look at these two for a second. What we've shown is that chlorine is the same element in both cases. In fact, there's 2 chlorines here and 2 chlorines here. But the oxidation number when chlorine is off as a diatomic molecule by itself is just 0. The oxidation number of chlorine when it has an oxygen in there, even though there's 2 chlorines, but when you bond it together like this, the oxidation number changes. It's different. So you can't, this is something we already know from doing all these problems, you can't just look at an element and know what its oxidation number is without using our prioritized rules. Because you might not predict that they will have different numbers. You might think, well, chlorine, yeah, usually it's -1, so I'll just pick -1. Not only is it not -1, it's not even the same, okay, different compounds. So let's go down this list and see what we can find out. So let's look at C. Here's Cl2O3. And I already gave you the punchline. You should expect them to be different. So let's just check it out. We have 2 chlorines. And now we have 3 oxygens, and each one's going to be -2, and the whole thing has to sum to 0. So 2 chlorines minus 6 is 0. So if we move the 6 over there, it'll be 2 chlorines is equal to +6. And then you divide by 2, what you're going to have is +3. So here the oxidation number of chlorine is +3 in Cl2O3. All right, so again, different than the ones above. All right, now let's just move up to the top of the board here and see if we can squeeze in the rest of what we're working on. Let's look at D, Cl2O7. Cl2O7. Let me switch to purple. And what we have here is we have 2 chlorines, 7 oxygens. Each one is -2 because that's how our list is working, and they all have to sum to 0. So here we have 2 chlorines. Let's just make sure everyone understands this is -14 or -14. Now we move the 14 over, and we divide by 2. So now we have an oxidation number of +7 in Cl2O7. So there the oxidation number is +7. And then we'll do the final one here. The final one is Cl2O5. And then when we do that, what we'll find is we have 2 chlorines, 5 oxygens, each one's -2, and then we have to get 0. So we'll multiply this, 2 chlorines, and then we'll move the 10 over, and then chlorine is going to be equal to +5 in Cl2O5. It'll be +5. So the point of this problem is very simple compounds. The point of this problem was mostly to tell you that chlorine, as an example, can have different oxidation numbers in different compounds. And that is really one of the most important things to pull out of this entire section and in the last few sections. Number one, you have this list here, this prioritized list that you have to go down. Number two, you kind of have some feeling up until now, based on looking at the periodic table, what a lot of different compounds are going to want to form. We know off the top of our head that hydrogen is going to mostly want to be +1. You know, calcium and potassium and the very reactive compounds, we know that they're generally going to want to do. We also know that oxygen a lot of times wants to be -2. We know that fluorine has certain things that it likes to do. But the point is you can't just remember that stuff and then throw it on your paper. You have to follow this prioritized list. And when you do, even with compounds that are very, very similar to one another, can yield oxidation numbers that are different. Okay? And again, when I opened the first section on oxidation number, I told you, in general, you can think of it as the charge that's bound up in there. Okay? In general, you can kind of think of it that way. But mostly, oxidation number is an arbitrary kind of bookkeeping method. We have a procedure, we assign these numbers. It's a bookkeeping method. Most of the time, it does correspond to the actual charge that we think is in there, but even sometimes you might get fractional charges or oxidation numbers, or you might get something weird that you don't expect. And the reason that sometimes you get that is because it's a bookkeeping method. What we're really going to be interested in is looking on both sides of the reaction, from the beginning all the way to the end, and seeing how the oxidation numbers change. The change in the oxidation number is really, really the most important thing. So it's not that important to know that the oxidation number on chlorine is +1 here, or that the oxidation number in chlorine is +7 there. That's not that important. What is important is when I have a real chemical reaction with something on the left and something on the right, and I can see that the oxidation number is like 5 over here, and the oxidation number is -4 over here, then I know the change in the oxidation number, and the change in the oxidation number tells me a whole lot. So we haven't gotten there yet, but knowing how to calculate these oxidation numbers is what leads us to be able to do that. So follow me on to the next section once you understand this, and we'll start looking at chemical reactions on the left and on the right, finding their oxidation numbers and using that information to learn about what's going on. And that is really the whole motivation behind everything we've been doing in the last few sections with oxidation numbers in redox reactions. Hello and welcome to the section of the Chemistry Tutor. Here we're going to put together a lot of the knowledge and skills that we've gained in the previous few sections with oxidation number. And we're going to use it to look at redox reactions and look at the change in the oxidation number from the left-hand side to the right-hand side. And we're going to use that to figure out what's being oxidized and what's being reduced. Now you can see and remember that before we did some of this sort of idea with half reactions, And that was certain, easier sort of things that we could use half reactions to go figure out what was oxidized and what was reduced. But the oxidation number method, which is what we're using here, can be used for really any chemical reaction, any redox reaction. And so what you're looking for is a change in the oxidation numbers of something. And if you don't have any change in any oxidation numbers of any elements anywhere in the reaction, then it's not a redox reaction. That means there's no electrons transferred, so it's not redox. And so when you see something increase or decrease in oxidation number, that's what you're looking for. So specifically, the definition of what we're looking for oxidation is very easy, actually. It's the increase in the oxidation number. So if oxidation is defined to be the increase in oxidation number, then reduction is defined to be the decrease in the oxidation number in a chemical reaction. This is really important stuff. And in fact, a lot of students, when they get in chemistry, they start getting confused because I already told you a definition for oxidation and reduction. I told you we went into excruciating detail that was talking about electrons being gained or lost. And then we talk about oxidation number, and then I'm giving you a different definition. So people say, what are you doing? What's right? Why are you giving me all these definitions? Well, it's just another way of looking at the same process. All right, and I'll say it again. There's just another way of looking at exactly the same thing. This definition is not in conflict with what you learned before. They're both true. It just turns out that assigning oxidation numbers is something we know how to do based on the rules that we have learned. So once we have those oxidation numbers, if we look on the left-hand side of the reaction and we see something that increases an oxidation number, it means maybe something has oxidation number 1 on one side of the reaction and it goes to oxidation number 7 on the other side. So it's increased in oxidation number, right? We know how to find these oxidation numbers. We can see if it increases, and if it increases, we know that entity that we're talking about has been oxidized. And we already talked before that anytime you have oxidation, you must also have a corresponding reduction, right? Because it's a gain and a loss of electrons. So it's all the same definitions, all the same concepts. If we see something that starts off with oxidation number of 3 and ends up with oxidation number -4, that means that it has decreased its oxidation number, and so it must undergo reduction. It's also a little easier to remember these rules because reduction means decrease in oxidation number, and oxidation is an increase in oxidation number. So that's basically what we've been doing up until now. So if you're given a half reaction that shows the electrons, you can figure out what's oxidized and reduced. But if you're not given a half reaction, sometimes it's tough to figure out what's been oxidized and what's been reduced. So in this case, you bust out everything and put an oxidation number for everything you have, and then you look at the changes, and then that tells you what's been oxidized. So let's take a simpler example, something that we know we can do quickly. So let's say we have hydrogen gas plus chlorine gas, and these are diatomic molecules that are gas, so we just put them as Cl2 and H2. And we say this yields 2HCl. So far this is a balanced chemical reaction. We have 2 hydrogens, 2 hydrogens, 2 chlorines, 2 chlorines. So it's balanced. But let's just say that we would like to know what's oxidized and what's reduced. So we don't have a half reaction here, and we don't have any ions anywhere to give us any clues like we had before when we did some of those half reactions. We don't have any clues to tell us what's gaining and losing electrons. We have some ideas from prior discussions, but we don't have a rock-solid technique to go figure out what's been oxidized and what's been reduced here. So the way you do it is you do it with oxidation number. So what I'm going to do is rewrite this reaction so I don't clutter up the one I have here. 2HCl. And so what we're going to do is we're going to use the same rules that we've done before. So here we have H2, and by now you should know that when you have something off by itself, like a diatomic molecule like this or just an atom by itself, its oxidation number is always 0 because the sum of the oxidation numbers in this molecule have to equal 0. Same thing here. So the oxidation number here is 0. So you can assign zeros right there. Now let's look at hydrochloric acid, HCl, and let's assign oxidation numbers. We've done this many times. We know the sum has to be 0. We look for group 1A metals. We don't have one because we don't count hydrogen as a metal. It has its own rule down here. We don't have any fluorines, but we do have an oxygen a hydrogen that has an oxidation number of +1. So now we can stop because we can figure out, now we know the sum of these oxidation numbers, forget about the 2 here, the sum of these oxidation numbers must be 0. Here we have +1, so that means that this one must be -1. So I'm not writing these on the board too quickly to try to just tell you, boom, I'm putting some on paper. I'm trying to show you that we're using the same methods for oxidation number that we've already been using. We just apply it to everything in this reaction. So now that we have everything down, you can see that for hydrogen, when you just compare it here, it goes from oxidation number 0 to oxidation number +1. So this is an increase. So this means that this has been oxidized because the oxidation number has increased. All right, and then also separately, we can go take a look at this guy here, chlorine. Okay, and we can see that the oxidation number goes from 0 to -1. So the oxidation number has decreased. So I'll write decreased here. So this is reduced. Or in other words, it's undergone reduction. So notice, just like everything else we've talked about in a chemical reaction, when you have an oxidation process, it must be accompanied by a reduction process. And that's what we have here. We have an increase in oxidation number. We also have something else that has a decrease in oxidation number. We have to have it that way. If you ever find out in a chemical reaction, it's a good nugget for you, okay? That you have an increase in oxidation number somewhere, but you don't have any decrease in oxidation number to indicate a reduction, then you've made a mistake, okay? Because you have to have that in a chemical reaction. You have to have an increase somewhere and then a decrease somewhere else. Indicates an oxidation somewhere, indicates a reduction somewhere. So you need to have both of those things. So just to spell it out, we'll just put it on like you would say on your paper. You would say hydrogen, H2, is oxidized. And we know it's oxidized because its oxidation number increased. Cl2 is reduced. Now these definitions, based on what we're doing here, is no different than what we've learned before. Because H2 is oxidized, we know that it loses electrons. And because chlorine is reduced, we know that it has gained electrons. So this gain and loss of electrons is exactly the same thing that we learned before. Whenever you look from 0 over here to +1, you can kind of think of these oxidation numbers being the charges, kind of. Like we said sometimes that it doesn't really make physical sense. It's a bookkeeping method. But you can kind of think of them as charges. So if you think of hydrogen having a charge of 0 here, and if you think of it having a charge of +1 here, how do you think that happened? How do you think it became and had a positive charge? Well, the way that happens is it loses electron. It loses one electron so that it has a net positive charge. So if it loses electrons, it must be oxidized because oxidation is a loss of electrons. The chlorine went from 0 to -1. How do you think that happened? Well, it gained an electron somehow. So it gains an electron, and that's what we call reduction. So this is all tying back with what we learned before. We're not really learning anything different other than a rock-solid, repeatable way to find out in the reaction what's being oxidized and what's being reduced using these oxidation numbers. So the bottom line is you use all the rules we've learned to find all the oxidation numbers on the left and on the right. And then if you have an increase, it's automatically oxidation, and if it's a decrease, it's automatically reduction. Now, one thing I want to point out, I'll say it a few different times, but I want to start saying it the first time here. I said a minute ago that if you have an oxidation process, an increase in oxidation number, then somewhere in the reaction there has to be a reduction process because redox, they go hand in hand. You have to have one with the other. You just have to, okay? Now in this case, the oxidation number went from 0 to +1, and then it went from 0 to -1. So we gained an oxidation number of 1, and we lost an oxidation number of 1, all right? The way the oxidation number stuff works, the oxidation number is per atom. So in this case, it just so happens that the plus and the -1 were the same, equal and opposite. But when you find your oxidation numbers in your reaction, they're not going to always be the same number, but just opposites of one another. That happened to be the case here, but it's not always going to be the case. So the punchline is, when I tell you that when you see an increase in oxidation number, you should also see a decrease in oxidation number, because you have to have redox going on. You have to have both processes going on. When I tell you that, I'm not saying you have to have +1 - 1, or +2 - 2, or +5 - 5. I'm not saying you have to have an equal and opposite reduction in oxidation number to balance the other one. What I'm saying is you just need to have a gain somewhere and a loss somewhere. The gain in oxidation number will be your oxidation process. The loss in oxidation number will be your reduction process. But those numbers don't have to always balance like they do in this simple example here. All you're looking for is a gain somewhere and a loss somewhere, and that's mostly what you're concerned with. We'll talk more about that when we get to balancing equations in a little bit, but I want to make sure and point that out. So the next thing we're going to do is do a little bit more complicated example of a different reaction where we're going to try to identify what's being oxidized and what's being reduced. So let's say you have NaNO3 plus lead, Pb, and it's going to be NaNO2 plus lead oxide, PbO. And what we want to do is figure out what is being oxidized and what's being reduced. Now again, we don't really know how to use half reactions here like we did before, because we don't know really the ions. We don't have that information really given to us ahead of time. So just by looking at the reaction, it's difficult to figure out what's gained electrons and what's lost electrons. So you turn to the oxidation numbers to help you find it out. So what we need to do is literally figure out the oxidation numbers of every single thing in this reaction. We have sodium, nitrogen, oxygen, lead, sodium, nitrogen, oxygen, lead, and oxygen. And we need to find out the oxidation numbers everywhere in this reaction for every element. And then we'll just look for changes. Some stuff will increase, some stuff will decrease. Some oxidation numbers will stay the same, which means those aren't participating and gaining or losing any electrons anywhere. So then once we figure that out, we know what's oxidized and what's reduced. So my advice is to write your reaction down, draw a little divider line under it, and then let's go figure out each term separately, because we have to use the rules that we have on the board for every term. And I know it's a little bit of a pain, but we really just have to do it that way. So for this, for rule number 1, we know the sum of the oxidation numbers has got to be equal 0, because this is a neutral compound. That's rule number 1. And then we go over here and we say, do I have any group 1A or 2A metals? And I do have a sodium, so I know right away the sodium, not N, that's nitrogen, Na is +1. So I know that that's the case. Then you ask yourself, do I have enough info to figure this out? And I don't, because I have 3 elements. So let's keep going down the list. Do I have any fluorine? No. Do I have any hydrogen? No. Do I have any oxygen? Yes, I do. So the oxygen is -2. So now you ask yourself, do I have enough information to solve and find the unknown? And I do now. Sodium is 1. Nitrogen is unknown. Oxygen, there's 3 of them, each with -2, and the whole thing has to sum to 0. So we're just doing the rules that we did before. 1 plus n minus 6 is 0. Add these together, n minus 5 is 0, so nitrogen has +5 oxidation number. Okay, so let's just hang on to that. Let's leave it there. We know that it's important, but we found all the oxidation numbers of this part of the reaction. All right, now for lead, what do you think is going to happen with lead? So let me draw like a little divider here. For lead, well, it's just one atom off by itself. It's neutral, there's no charge on it. So we should know by now the oxidation number of things just hanging out by themselves when they're neutral is just 0. So there's nothing else I have to do. I don't need to follow any more rules. That's just kind of given there. All right, the next thing we're going to look at is NaNO2. And we're going to follow all the rules that we did for the last time. So let's go and do the same process again. We know that the sum of the oxidation numbers has to equal 0 because there's no charge, it's neutral charge. And we're going to go down, it's very similar to before. Do we have any group 1 or 2 atoms? And we do. So we know that sodium is going to be +1. Then we go down the list again. Do we have any fluorine? Do we have any hydrogen? But we do have oxygen. So we're going to go into oxygen, and that's going to be -2. And we ask ourselves, do we know enough to finish solving this guy for the unknown? And we do now. So sodium is 1. Nitrogen's the unknown. 2 oxygens, each with oxidation number -2, and it has to sum to 0. So what we have is 1 plus n minus 4, 0. We add these together, n minus 3 is 0, n is positive 3. So that's important. So I have the oxidation numbers for everything here. I have the oxidation number of this, and I have the oxidation numbers of everything here. The only thing that really remains is the oxidation number of the lead oxide. So what I'm going to do to kind of keep room on the board is I'm going to kind of draw a little dividing line here, and I'm going to do that one right under here. Right? So what we're going to do is look at PbO. And again, we do this exact same process. So the first thing, number one, this has no charge. It's a neutral, so the sum of the oxidation numbers has to equal 0. The next thing is we go down our list. Do we have any group 1 or 2 metals? No, we don't. Do we have any fluorines? Do we have any hydrogens? No, we don't. Do we have any oxygens? Yes, I do. It's a -2. And I'm starting to erase this accidentally, so this is -2 here, like that. So we have the -2, so what we have is oxygens, -2, and now we have enough, using math, to figure out what the lead is. So lead, plus the oxygen, so we'll say plus -2, is 0. And now I'll just move this over here, so lead is +2. So now I have an oxidation number for every single thing in this chemical reaction, every element everywhere. So now what I'm going to do is I'm going to rewrite the reaction so I don't clutter up what I have. I have NaNO3, so I'll put an O3, plus Pb yields NaNO, make it O big, 2 plus lead oxide, like this. And now what I suggest you do, instead of trying to just look at these numbers everywhere, is try to put the oxidation numbers where, like right on top of the reaction. So here we found everything here. So the sodium was +1, the nitrogen we calculated +5, oxygen was -2. Lead was 0. Over here we calculated that this was +1, the nitrogen here we calculated +3, the oxygen was -2. Here we calculated the lead was +2, and the oxygen was -2. So you see what I'm saying? We have the reaction and we literally assign oxidation numbers to every single element in every compound of everything in the reaction. And then we start comparing to try to figure out what changes, okay? And right away we see that sodium has +1 oxidation number. Over here, sodium also still has +1 oxidation number. So the oxidation number of sodium is the same on the left and on the right-hand side. There was no change. There was no increase, and there was no decrease. So that means sodium was not oxidized, and sodium wasn't reduced. Sodium didn't really do much of anything, and according to this, sodium didn't really become oxidized or reduced, and that's the whole point here, all right? So then we look at nitrogen. Nitrogen had a +5, and then it went to a +3. So let's note that we have nitrogen actually had a change in oxidation number, went from 5 to 3. So this is a decrease. So this means, since it was decreased, this underwent reduction. This nitrogen underwent reduction. So let's keep looking. The oxygen was a -2, the oxygen over here was a -2, and the oxygen over here was also -2. So oxygen didn't have any change in oxidation number. And we look at lead. We had 0 oxidation number, but then we ended up with +2 oxidation number. So there is a change here in oxidation number from here to here. And lead went from 0 to +2, so this is an increase. So that means that it was oxidized. All right? So what you should pull out of this is a couple of things. All right? First of all, there was a decrease in something's oxidation number, which means that it was reduction. There was also an increase in something else's oxidation number, which means that was oxidized. All right, so there always has to be something increasing to give you that oxidation there, and then there has to be something decreasing to give you that reduction. It's very, very important that you see both. Everything else, there was no change. Sodium was the same, oxygen was the same. And if I have a reaction 1,000,000 miles long, once I identify what's increased and what's decreased, everything else really should just be hanging out, all right, and not really being oxidized or reduced. So because the problem asked us, let's just write it all down. What we're going to say is the lead, Pb, was oxidized. Right? Oxidized. And if you remember back to your definition, that means it was losing electrons. Now, when it's oxidized, we can also say that Pb is the reducing agent. You know, a lot of times on tests, they'll tell you, they'll give you a reaction. They'll say, use oxidation numbers to find out what was oxidized and what was reduced, and what was the oxidizing agent, what was the reducing agent. First step is figuring out what was oxidized. Whatever was oxidized, you automatically know it's the reducing agent. You flip the word to the other side and you call it the agent. That's kind of what I was telling you from before. All right, and now we need to figure out what was reduced. So here we have this whole thing here. The nitrogen was really the thing that changed. You don't say that nitrogen was reduced. I mean, nitrogen's in there, and nitrogen is what, you know, did change in terms of its oxidation number. But when you think about it, this thing here, this NO3, is a polyatomic ion, right? So really what you typically say is NO3, this ion that ends up being the thing that participates here, and when you do this in solution, this ion was reduced. Okay, so that's what you typically actually write down and say that was what was reduced. The nitrogen is the thing that has the number that changes, but really it's this whole thing that is doing the participating, because this is a negative ion and this is a positive ion, so this is the thing that actually ends up gaining the electrons to be reduced. Okay, and then what you say, if you want to find out what the agent is, you'll list this NaNO3 is the oxidizing agent. Now this is just convention. It's just something that some textbooks do and some textbooks don't, some teachers do and some teachers don't. When you list the agent, when you list what is the oxidizing agent, what is the reducing agent, typically you list the whole compound. So even though it was just this part that changed, we list the whole compound as the oxidizing agent or the reducing agent. Typically when you list what is oxidized and reduced, you focus on the element or the little ion, the polyatomic ion that's part of it. It wouldn't be totally wrong to say that this was reduced, this whole thing was reduced. It wouldn't be wrong. It's just some textbooks are different, some teachers are different. So typically what I'm going to recommend is you identify the ion. By now you should realize that NO3 is a polyatomic ion with a negative charge. This guy is almost like a unit, so this is the thing that's reduced, so you kind of focus on that, and then the whole enchilada is what is the oxidizing agent. All right. Those are kind of splitting hairs. The most important thing for you to know is the change in oxidation number tells you that. You don't just say, well, nitrogen was the thing that was reduced. You don't pull that atom out because nitrogen is not behaving by itself. Nitrogen's bound up into this polyatomic ion, and it behaves as almost like a little unit that floats around. I mean, you can see that the nitrogen and the oxygen kind of hang out together over here too, but it's slightly different as NO2. So it behaves as a unit is what I'm trying to say. So you get practice with this as you work problems. The most important thing is identify all the numbers, look for the increases and decreases, and then you write down what was oxidized and what was reduced. So make sure you understand this, and then follow me on to the next section where we're going to work some more problems and give you a lot more practice with identifying oxidation and reduction using these oxidation numbers. It really is the most bulletproof way to figure out what's going on in a redox reaction. And for complicated reactions like this, it's really the only way to figure it out without just guessing, and we're not into guessing. So use your rules, assign your numbers, figure out what's increased and decreased, and that will tell you what's oxidized and reduced in a redox reaction.